Give the third mini course this week, and his is going to be on higher dimensional Fano varieties. So,
okay, thank you for the introduction, and thank you everyone for coming. So this is actually my second time in Brazil. The first time was for Math Olympiad. It was Olimpiada del Cono Sur in around 16 years ago. So I'm happy to be back, and for the second time, it's also math related. So yeah, so I will talk about higher dimensional Fano varieties, and the schedule will be more or less the following. So today, I will give an introduction to Fano varieties. So I'm sorry that this will be a bit boring for the experts. But maybe I will actually mention some new perspectives. So the second part is about log terminal singularities, and here I will, so this will be tomorrow, and here I actually will present some new results about log terminal singularities. So then I will proceed to talk about singular Fano varieties. So in the first talk, I will just restrict myself to smooth projective varieties. So the third talk on Thursday will be about singular Fano varieties. And finally, on Friday, I will talk about cluster Fano varieties. And this is entirely new, so there is just very few papers on arXiv on this topic, and I will explain you what it is about if the roof doesn't fall today. So let's start with the introduction to Fano varieties. And first, let me speak about the smooth projective variety. So I will try to explain things in details and not go into technicalities very fast. So if you have X smooth projective variety, so a way to study smooth projective variety, so a way to study geometric objects is by endowing them with some functions. And the functions that we like the most in algebraic geometry are line bundles, right? So essentially, one way to try to study a given geometric object or algebraic variety is by trying to study all the possible line bundles on it, right? And if I tell you about studying all the possible line bundles on a variety, well, first I have to give you one, right? And you can take the trivial one, but that one is not so interesting. So there is a canonical way to endow any smooth projective variety with a line bundle, and it's the following way. So first you start from the tangent bundle. So let's say projective variety of dimension n. And then you take Tx to be the tangent bundle. You can take it with respect to some projective embedding of your choice. And then after taking the tangent bundle, which is actually a vector bundle of rank equal to the dimension of the variety, you can take the cotangent and then take the top wedge of this, which we call the canonical line bundle. So this is the definition of the canonical line bundle, is the top wedge of the cotangent. And now I gave you a line bundle for any smooth projective variety, and it's called canonical line bundle because it's actually, so canonical line bundle, it's actually canonical from X. So for different embeddings and different, let's say, representations that you can pick of the tangent, then you will end up with isomorphic canonical line bundles. So it's a line bundle that is canonically attached to X. Okay? And then you can find something that we call the canonical divisor on X, which is the unique up to linear equivalence divisor that makes omega x isomorphic to OX kx. And this divisor here, this Cartier divisor on X, is called the canonical divisor. Okay, so studying the canonical divisor is sort of analogous to studying the canonical line bundle. So then we have a trichotomy. So essentially, we can study how positive the canonical line bundle of a smooth projective variety is, right? So if you do topological manifolds, right, it may happen in topological manifolds, actually it always happens, that a vector bundle is isomorphic to its dual. In algebraic geometry, in complex algebraic geometry, that never happens, right? So if a line bundle is isomorphic to its dual, then it's actually OX, it's the trivial line bundle. So we can talk about positivity of line bundles or negativity of line bundles in algebraic geometry, something that we cannot do for topological manifolds. So the way that we measure it is by asking ourselves, does omega x or tensors of omega x have a lot of sections or not? So then we have the following trichotomy, which is not really a trichotomy. We say that X is Fano I will write in quotes the object that I'm defining, is Fano if omega x to the negative m is very ample for some m large and divisible enough for some m. And notice that I'm writing to the negative m power. So I'm dualizing first and then taking the mth power for some m divisible enough. Well, you can say large enough. It doesn't really change the definition. So we say that x is Calabi-Yau, quotes Calabi-Yau, if some power of omega x is actually trivial, so isomorphic to OX, and we say that x is canonically polarized if some positive power of the canonical line bundle is very ample. Canonically polarized if omega x to some power is very ample. Oh, m larger or equal than 0 here to make it very negative, and here m larger or equal than 0 for very ample for m divisible enough. You can write large enough in these definitions. You don't change anything. So essentially, these are 3 pure classes of algebraic varieties, right? The motto of birational geometry is that essentially you can transform every algebraic variety, any smooth projective variety, you can transform it birationally into a new one, which is favored by one of these 3 classes. So in other words, I don't want to enter in any technicality, these 3 classes of algebraic varieties should be the building blocks of all algebraic varieties, okay? So if we understand, so you can think about this as the prime numbers in algebraic geometry, okay? You want to write everything as products of this. And it is more or less true that it's possible, up to some big conjectures, of course. So let me write the following table. Before getting deeper into Fano varieties, let me write a table that explains the behavior of these varieties with respect, of these classes of varieties with respect to different geometric aspects. So sorry, I will erase this one. I need more space for my table. So let's write the following table. So here we will start with the 3 classes. So Fano, Calabi-Yau, and canonically polarized. Fano, Calabi-Yau, and I will just abbreviate canonically polarized by this. And then you can ask me what happens in dimension 1. So in dimension 1, a Fano variety, a smooth projective variety of dimension 1, which is Fano, is just isomorphic to the projective line. And I forgot to say this, and I think the 2 previous mini courses too, that I'm working over the complex numbers. Okay, so everything is over the complex numbers, but I think everything I will say, almost everything I will say, works over algebraically closed fields of characteristic 0. So in dimension 1, there is only the projective line. So if you look at Calabi-Yau curves or Calabi-Yau varieties, smooth projective varieties that are Calabi-Yau of dimension 1, then you get elliptic curves, right, that are algebraic, not algebraic, sorry, real tori. And then if you look at canonically polarized, so here the genus is 1, here the genus is 0, and canonically polarized for curves is the same as higher genus curves. So genus at least 2. So this is what happens in dimension 1. So then let's study a different aspect. So let's see what happens for the fundamental group of these varieties. Oops, that's a very ugly pie. Let me try again. So what happens for the fundamental groups of these varieties? So Fano varieties are simply connected. So smooth Fano varieties. So remember that today everything is smooth. And this is actually a term due to Kobayashi in the 1970s. If you look at a Calabi-Yau variety of dimension n, then the fundamental group is virtually nilpotent. Actually, I can say virtually abelian of rank at most twice the dimension of x. And this is a theorem due to Gromov and Cheger in the 80s. Sorry, I don't remember the precise dates. And for canonically polarized varieties, actually we don't know what to write here yet. This is This? Yes, yes. I mean, I think this was conjecture even around the 60s. The way that they prove this is with differential geometry, because I'm in the smooth world. Actually, there is no algebraic proof of this fact yet. And if you go to an algebraically closed field of characteristic 0, this is an open problem to prove that the fundamental group of Calabi-Yau, let's say a mildly singular Calabi-Yau varieties, is virtually nilpotent. So what this means, virtually abelian of rank at most 2 dimension of X, it means that there is a normal subgroup which is abelian of rank at most twice the dimension, and the co-kernel is a finite group. So up to a finite cover, you get this nice fundamental group. Okay? So let me try to move this. Okay, that's not too bad. Okay, so let's look at some different perspectives. For instance, automorphism groups of these varieties. If you look at automorphism groups of Fano varieties, you get linear algebraic groups. Okay, so you know, like algebraic tori, PGLN, and all these kind of things. Yes?
You can try to move it closer to the wall.
Sure. For security? Okay, good. Yeah. So, no, don't worry, that's fine. So if you look at automorphism group of Calabi-Yau varieties, again, I will say that this is an open problem to see what we have to write here. I mean, there are a lot of crazy examples that are not finally generated, and so on. So if you look at automorphisms of canonically polarized varieties, these are finite. So every canonically polarized has finite automorphism group. So if you look at not automorphisms, but let's say self-maps that are one-to-one almost everywhere, what we call in algebraic geometry birational automorphisms, the situation gets much more complicated for Fano varieties. So let's say that here let me just say that Cremona groups appear, and Susanna Zimmerman will be talking a lot about this next week. So Cremona groups appear, meaning that, so what I want to say is that here you can find some monstrous groups that are very, very far from being linear algebraic. Birational automorphisms of Calabi-Yaus, again, no one has any clue of what to write here to say something meaningful. And the birational automorphism group of a canonically polarized variety is again finite. So then if we look at high degree endomorphisms, so functions from X to X that have high degree, meaning not automorphisms, so high degree endomorphisms, then a Fano variety, so this is conjectural, so I will use a different color. I will use red in this table for conjectural statements. So there is a conjecture that says that if you have a high degree endomorphism on a Fano variety, then the variety must be toric. So only for toric varieties. So let me not get, I will define toric varieties in a second, but for the grad students, for instance, you can take the following morphism, right? You can take the morphism that goes from P2 to P2 and just square all the, not the square, but take the power of all the coordinates. This is a high degree endomorphism, right? And essentially, the conjecture says that if you have a high degree endomorphism on a Fano variety, then the variety must be toric. It doesn't tell you that it must have this shape, but at least the underlying variety must be a toric variety. So the endomorphism may not be toric. So if you look at a high degree endomorphisms on Calabi-Yau varieties, then the conjecture is that it must be abelian. So again, it must be related to multiplying everything by n in some way. So only for abelian varieties. And it is known that there is no canonically polarized with high degree endomorphisms. And finally, one can think about, let's say, a number theory perspective. So you can think about the rational points of the variety. So which points are defined? Each coordinate is defined over the rational numbers. So in this case, let me write here in red. It's not conjectural, but it's more complicated to state that most of the time you either find dense set of rational points on a Fano variety or empty. It really depends on the field of definition of your variety. Like for instance, if you just take P2 and then you define the subvariety x not equal 3, then it has infinitely many rational points. But if you define the linear subvariety x not equal pi, you have no rational points because you choose the first component to be transcendental. So it really depends on the fields of definition of your variety. So for the second row, we again have question marks, right? For elliptic curves, this is something very hard to understand. And for canonically polarized varieties, we expect that XQ is contained in a proper, this is conjectural again, so let me use red. So this is contained in a proper Zariski closed. And this is known by in dimension 1 is a theorem due to Faltings. And I think in higher dimensions, this conjecture is due to Lang, containing a proper Zariski closed. So this table is just to explain to the students that Fano varieties, Calabi-Yau varieties, and canonically polarized varieties behave very different from different perspectives. Like sometimes, for instance, from the topological perspective, let me write here topological because this is pretty much topology. Let me write dynamics here. And finally, number theory. Right, so let's say the following phrase makes a lot of sense for me after having this table. So from the topological perspective, Fanos are the simpler ones, and canonically polarized are the most difficult ones to study. From the perspective of dynamics, it gets flipped. Canonically polarized are the simpler ones. They don't have interesting dynamical systems. But the Fano ones gets very complicated from the dynamical point of view. And in the number theory perspective, then gets flipped again. Calabi-Yaus are the most complicated ones. We don't even have conjectures about how to describe the rational points of Calabi-Yau varieties. And the other two, well, they could be complicated or simple, depending the example you pick. Okay, so this was just a table to explain that, even studying these three pure classes of algebraic varieties, Fano, Calabi-Yau, and canonically polarized, is interesting from many different perspectives. Even today, you see there is a lot of question marks in the board, right? So there is a lot of research trying to understand these pure classes of algebraic varieties. But today we will focus on the Fano ones. So why are we going to focus on Fano for this week, or why we have been focusing on this kind of varieties for the last few decades, or at least a bunch of us, is because there is this sort of philosophy that there is less Fano varieties than Calabi-Yaus and canonically polarized. So let me, right, in the case of curves, there is just one Fano variety, right? And there are infinitely many Calabi-Yaus, right? All the elliptic curves, so they form a one-dimensional family that has moduli. So next I will give you examples, more examples of these three classes of algebraic varieties. And before I jump to the next section, are there any questions or comments about this? Okay. Yeah, but it's not high. It will be only high degree in some components. So when I say high degree, I mean, yeah, so what I mean is that the degree must be high with respect to all the variables, right? So if you take a product, then it will be sort of linear in some set of variables, or constant in some set of variables, and high degree on the other. So yeah, the right wording is polarized endomorphism, but I didn't want to. Yep. Okay, so. Yeah, so how to construct examples, right? So this is the question that the students may be wondering now. So there is a formula called adjunction formula that tells you how to compute the canonical line bundle of a hypersurface inside some ambient space. And from this formula, one can cook many examples of Fano varieties, Calabi-Yaus, and canonically polarized. So example, if we take a smooth hypersurface, so if XD inside Pn is a smooth hypersurface, then omega xd, so d here is the degree, so I forgot to mention this, of degree d, then omega xd is omega Pn plus OXD restricted to XD, and this is equal to the canonical line bundle of Pn is negative n minus 1, the class of a hyperplane. XD is just equivalent to d times a hyperplane, so we get the following expression. So this is equal to d minus 1 minus n h restricted to the hypersurface. So from this computation, you can see that something happens around n plus 1, right? This becomes positive or negative, and that's precisely the trichotomy that we're talking about. If d is larger than n plus 1, this is a positive multiple of an ample divisor, hence its restriction is ample. so the canonical will be ample. If this number is negative, this is a negative multiple of an ample divisor, so it's anti-ample, it's negative, some power of its negative is very ample, so the variety will be Fano. And then if d minus 1 minus n is 0, meaning d equals n plus 1, then omega xd will be 0, so you will get a Calabi-Yau variety. So we get the following, and this is why the previous board was called, no, 2 hours ago I call it the trichotomy because for hypersurfaces, actually a trichotomy. So if d is less than n plus 1, xd is Fano. If d is equal to n plus 1, xd is Calabi-Yau. And if d is larger than n plus 1, xd is canonically polarized. So what I want to say here is that this picture should give you the feeling that there is less Fanos than Calabi-Yaus, and of course, much less than canonically polarized. Because even though you have more degrees of choice for the Fano ones, you have to choose equations of a smaller degree, so there is less coefficients that you can move around. So asymptotically, the medium one wins. Yep. So give me a second. I made a mess with my notes. OK, good. I'm here. So now let's discuss what happens in dimension 2. So let's try to now start understanding the classification of Fano varieties. So this tells me that if I want to understand Fano surfaces, well, one source of example is hypersurfaces of low degree, right, in P3. So from the example, I get that if you take any hyperplane in P3, you get a Fano surface. If you take any quadric in P3, you get another Fano surface, smooth. Both of them are smooth. Well, this one is a hyperplane, so it must be smooth. And then if you take a cubic surface in P3, then this is also Fano, right? There are all numbers less than 4. So how they look like? So this one is just isomorphic to P2. This should not be surprising. You can take it as an exercise. So this one is actually not so trivial to see that it must be always isomorphic to P1 times P1. Here you have to use some theory of quadratic forms and write the quadratic form as just some sum of squares and then do a change of variable. But it's not hard to prove that any smooth quadric in P3 is isomorphic to P1 times P1. So what happens with cubic surfaces? And actually, this is something that was studied by the Italian School of Algebraic Geometers in the 1920s. So what they realized is that it doesn't matter what example of cubic surface you pick, it always contains 27 lines, which was something very surprising for them. And I guess it's surprising for everyone. So you can take an example. Just take the sum of the cubes of the coordinates of P cube and try to find the 27 lines. That's a fun exercise. OK, so what they observe is that X3 inside P3, so the cubic surface, a smooth cubic surface, always contains 27 lines. Always contains 27 lines. So what do I mean with line? Just like literally a line inside P3, like a linear copy of P1. And then something that was even more surprising is that they realized that it doesn't matter which example of a smooth cubic surface they took, there was always 6 skew lines. So meaning that they didn't intersect each other, 6 pairwise skew lines. And then they were trying to understand what happens if you sort of delete these lines from the picture. So the Italian algebraic geometers came out with the notion of blowdown, which essentially takes some rational curve with a prescribed normal bundle and map it to a point. And they realized that if you blow down these 6 skew lines, you get to the projective space, to the projective plane. So the Italian School of Algebraic Geometers realized that X3, any X3, is the blow up of P2, is the quotes blow up. I haven't defined this word. Let me not get into the details of this. Blow up of P2 in 6 points in general position. So this was the way that they realized about this. And where are the 27 lines, right? So I mentioned that it contains 27 lines, so let's try to do the countings. And 2 out of 3 times that I give a talk like this, I do something wrong counting the lines, and I don't get 27. So let's hope this one is the right one. So you blow up the 6 points, so let me just draw 6 points. And let's imagine that the board is P2, right? So what is a line? So essentially, a line here is, well, let me not get into the details. And instead of counting lines, let me count rational curves with self-intersection -1, which a posteriori, they will turn out to be lines in this X3. But let's do the following counting. So let me pick a different color. So well, if you pick a line through 2 points, then L squared is equal to 1. Right? But once you blow up the 2 points, so each time that you blow up a point, you will reduce the self-intersection by 1. So this will be a -1 curve in X3 after you blow up these 2 yellow points. So the strict transform of this line in X3 will actually be a line. And then if you take a conic through 5 of the points, and I'm getting nervous that I will miscount again. So if you take a conic, then the square of the conic is 4, but then if you blow up the 5 points, then the square of the conic becomes -1. And you can show that this will give you another line in X3. And finally, you have 6 lines, which are the exceptional divisors of the blow-ups of these 6 yellow points. So let's do the counting, fingers crossed. So 6 exceptionals, which are the curves that are not in the picture. 15 strict transform of lines, strict transforms of lines, and 6 conics, right? Conics through 2 points of the 6. Wait, through 5 points. Okay, 21, 27, good. Yeah, we got at least the 27 -1 curves, and these turn out to be lines in X3. So, and then the Italians got interested in trying to classify all Fano surface, smooth Fano surface. And the main theorem is the following. So this is from 1920s. So let me state the theorem here. So essentially, all smooth Fano surfaces are obtained in a similar manner. So you have to start from P2, and then you have to blow up to 8 points. So that's the way to obtain almost all of them, except one, which is P1 times P1. So the theorem becomes the following. Theorem, any smooth Fano surface, which are called also Del Pezzo surfaces, any smooth Fano surface, these are also called Del Pezzo. I think maybe it was Del Pezzo who classified them. Is either isomorphic to P1 times P1, or the blow-up of P2 in at most K, well, let me say at K at most 8 points in general position. So this means that there are 10 families of smooth Fano surfaces. And these are all of them. So in dimension 1, there is just one, the projective line. In dimension 2, there are 10 families, P1 times P1, P2, the blow-up of P2 at a point, the blow-up of P2 at 2 points, and so on, always asking that the points are in general position. So are there any questions so far? Okay, so what time is it? Okay, I think I'm going fine. So let's discuss a little bit about the automorphism group of this variety. So I won't use this right now, but I will use it later today. So let's discuss the some invariants of these varieties. Okay. Questions? Okay. So one can attach some invariants to these varieties. for instance, its volume. So essentially, the volume tells you how does the sections of the anti-canonical systems grow. And one can show that for a Fano variety, or for a smooth Fano variety, the volume of a smooth Fano surface X is just the square of the anti-canonical divisor. So this is the definition of volume, and we set volume of X equals to this number. So essentially what happens here is that every time that you blow up P2 at a new point, the volume decreases precisely by 1. So let me draw another table. So here I will write a smooth Fano surface. The smooth Fano surface. Then volume. And finally, its automorphism group. So the group of, let's say, isomorphisms from X to X. So if the one that has the largest volume is P2, that has volume 9, right? So the anti-canonical is 3H, 3H squared is 9H squared, H squared is 1, so you get volume 1. And the automorphism group is just P, is PGL3C. Right, so it's a pretty large automorphism group. It contains a two-dimensional algebraic tori inside. So you can take the coordinates of P2, x0, x1, x2, and then you can multiply the last two by any two given complex numbers, non-zero complex numbers, and that gives you a GM square action on P2. So then let's see the other examples. So if you look at Del Pezzo surfaces or smooth Fano surfaces of volume 8, you get two examples. You can either pick the blow up of P2 at a point, or you can get, or you can take P1 times P1. So these two have volume 8, and what are their automorphisms group? So I don't remember the one of the blow up of P2 at a point. So let's say some connected group of rank at least 2. So with rank here, I mean rank of the maximal torus. So let me explain why you still have a torus action on this one. Because you can always pick an automorphism and assume that the point P is 1, 0, 0. So the automorphism, that the torus action that I described on P2 will lift to the blow up of this point. So you get a connected group of rank at least 2 is actually, I mean, you can define it, I mean, you can say that it's the subgroup of PGL3C fixing P. So it's some connected algebraic group. I don't remember precisely how to write it. This one I remember. So this one is just PGL2C times PGL2C, an extension with the shifting of the two coordinates. So GL2C, and this is an extension with Z2. So this is another pretty large algebraic group. Then if you blow up, then you can take the blow up of 2 points, and the volume will be 7. And again, I don't remember what the automorphism group is, but it's a connected group of rank. Connected, it's a linear algebraic group, actually, sorry. Linear algebraic group of rank. At least 2. So if you take the blow up of 3 points, and I'm not going to write all these steps of the table, so we'll finish here. So this, here you have volume 6. And the automorphism group is GM squared, semi-direct sum with S2 times S3. And if you pick any other element, any other row in the table, so if you pick volume 5 or below, meaning that you blow up at least 4 points in P2, then the automorphism group is finite in this step and all the ones below. So there is still quite a lot of research of understanding which finite groups can act on the Del Pezzo surface. I think it's completely classified over the complex numbers. But maybe in posit characteristics, there is still a few cases that we don't fully understand. So everything I want to mention is that the Fano surface, the smooth Fano surface with the largest volume is P2, and is also the one with the largest automorphism group. And as you pick Fano surfaces with a smaller and smaller volume, in which in this case are blow-ups of P2, then the automorphism group will start shrinking. And at some point, this will become finite. So I will come back to this picture to this table in a few minutes, but that's probably everything I want to say about the smooth Fano surfaces. So the title of these lectures is Higher Dimensional Fano Varieties, and so far I have talked about curves and surfaces, so let's go up. Are there any questions, comments, complaints? Yeah, I'm not sure if these are connected, okay, but we can check that later. The important thing is that they contain a torus. That's the only, maybe I meant to write. Sorry? Oh, yeah, I think you're right, yeah. Okay, so what happens in higher dimensions? So there is like a, let me start telling you one of the main theorems, which is Kolar-Miyaoka-Mori in 92. So, but before stating the theorem, let me explain something that I think should have been mentioned, which is the definition of bounded family of varieties, or you can say schemes if you want. So we say that a class of varieties is quotes bounded if there exists a finite type morphism, well, let me say projective morphisms between finite type schemes. A projective morphism. Because if I just say finite type morphism, someone will complain about the base not being finite type. Okay, between finite type schemes, let's say chi to t, such that for every x in C, we can find a point t in T. So I'm not saying close point or anything, just some point, such that xt is isomorphic to the fiber over T. So this is what we call a bounded class of varieties. I usually use the term class of varieties because sometimes this definition works independently of the field. So it's not really a set because the field can be arbitrarily large, so it's not a set. The cardinality is unbounded, okay? But so a way to restate the theorem that we just learned, this classic theorem from Italian algebraic geometers, is that the class of Del Pezzo surfaces, or the class of a smooth Fano surfaces, is bounded. And actually, this is true over any algebraically closed field and even fields of characteristic, positive characteristic, 0 or positive. Okay. So this is the statement that was proved by Kolar, Miyaoka, and Mori in every dimension. That if you look at all n-dimensional Fano varieties, so this was proved in 92 by Kolar, Miyaoka, and Mori, that they proved that the class of n-dimensional, smooth Fano varieties, well, and of course I have to fix n. So fix n a positive integer. Then the class of n-dimensional smooth Fano varieties is bounded. So what this means that if you look at all, for instance, complex smooth Fano threefolds or fourfolds or fivefolds, as long as you fix the dimension, there are finally many families that parameterizes all of them. Okay, so let me mention a caveat about this. I'm not asking every fiber of this family to belong to C. So you may have an example in which the fibers parameterizing elements in C is not algebraic inside T. We still call it bounded, okay? So this is a caveat, something that sometimes confuses people. So what is the idea of this theorem? So the way that they prove it is that they essentially prove that for any variety, any n-dimensional smooth Fano variety, you can control some m. So you can control this m such that this linear system is very ample. And this M is controlled in terms of N. And then essentially the argument goes, after you control this M, the argument is just some, let's say, Hilbert scheme arguments saying that all subschemes of Pn of some projective space of fixed degree forms a bounded family, and this will be a subset of that one, so then you're done. But then, of course, the difficult part is controlling this M in the proof. And I do not remember the bound that they give, but they give a bound which is like a exponential and has some factorials on it. It's extremely ugly. It's nothing near optimal. Okay. So that's the next question, and it's a question that has attracted me quite a bit. Is can we understand some asymptotics of smooth Fano varieties? And this is one of the topics that I will discuss this week. There are no answers, but okay, maybe some little ones. So that's something that we would like to understand, right? So in dimension 1, there is just one family, because there is just one isomorphism class. In dimension 2, there are 10 families. In dimension 3, I will tell you the answer in a second. What happens if you look at these families asymptotically? Can we say something? Can we have an upper bound for the number of families of smooth Fano varieties? So the answer is that it's way too hard for us. I think that we're not going to see an answer of that question, at least in this century. But we can do something. We can tweak the problem a little bit to try to make it manageable. Okay, so now the next natural question, right? So this is the question that you ask yourself if you're a grad student, you're learning this topic, is that in dimension 2, when we were studying smooth Fano surfaces, they're all blobs of P2. Right? So the question is, are all smooth Fano trifolds blobs of P3? Right? I mean, it works in dimension 2, works in dimension 1. It should work in dimension 3, right? So this is actually not true. So let me introduce the next definition. So we say that a variety is rational if it is birational to the projective space. So a variety X is quotes rational if X is birational, so meaning that you can get from X to the next variety, to Pn, for some n. Okay, so essentially this means that you can get from the projective space to X doing birational transformations, doing blow-ups, blow-downs, blow-ups, blow-downs. Okay? So then the question becomes, are all Fano varieties rational? And actually, the answer was given by Fano, but the proof was wrong. So there is a theorem in 72, and actually the approach by Griffiths and Harris has nothing to do with Fano's approach. Iskowski and Manning give an argument showing that Fano's approach actually does not work at all. So, but he did get the right answer, and that's actually valuable in mathematics. So Griffiths, Harris. 72, a smooth cubic threefold. So a smooth hypersurface defined by equation of degree 3 in P4 is not rational. Sorry? Oh, sorry. Thank you. Clemens. I did my pitch in Utah. I should. Yeah, please delete this part of the recording if you post it somewhere. It's not rational. Okay, so this tells you that there are Fano varieties, smooth Fano threefolds that are not, you cannot get to the projective space doing birational transformations, right? So then, I mean, this poses more questions, right? If you look at Fano varieties asymptotically, all smooth Fano varieties, and then you look at the rational ones, like how the ratio behaves. And this is a question that, again, we have no clue. So now let me start talking briefly about some special class of rational varieties which are very important in algebraic geometry and are called toric varieties. So this is a very special class of Fano varieties. So this was just to explain that not all Fano varieties are rational. Actually, it is expected that smooth hypersurfaces, or at least very general smooth hypersurfaces of degree at least 3, in dimension at least 4, they're all irrational, meaning that they're not rational. But these conjectures are extremely hard, and a lot of people have tried to prove them. So far unsuccessfully. So let's see. So definition. So we say that a normal projective variety X, a normal projective variety X is said to be toric, quotes, toric, if there is a dense open set, there is a dense open set of X, isomorphic to the n-dimensional algebraic tori, so isomorphic to GMN, and the action of GMN on itself extend to X. On itself extends to X. Okay, so this is a very special class of rational varieties. They're rational because they contain a copy of the algebraic torus. And it is very important in algebraic geometry because we can understand these varieties mostly combinatorially. So the way that you attach a combinatorial object to a toric variety is by doing the following procedure. So I'm not going to explain the whole dictionary between toric varieties and polytopes in full details, but at least let me tell you more or less how it works. So inside the algebraic tori, you have a lot of one-dimensional tori. So, oops, did I break something? No. So inside GMN, for instance, inside GM squared, you have a lot of copies of GM. For instance, you can take the parameter T going to T alpha, T beta for any alpha and beta. Right? So essentially, the copies of GM as a subgroup inside GM squared form a lattice. And then you can start looking at all these one-parameter subgroups and looking at the following points. So you look at the limit of X going to infinite of, let's call this map phi alpha beta of phi alpha comma beta T X. So since X is a projective variety, so my definition of toric is just for projective varieties, this must land inside X. So you can essentially get a partition of the lattice such that in every set of the partition, all these limits are the same. So if you start in the projective space and you start taking these limits, you will only get to 3 points, 1, 0, 0, 0, 1, 0, 0, 0, 1. And the partition that you get of the lattice, well, it depends on the choice of the lattice that you make, right? So you can always act by GL2, but if you pick the torus action that I mentioned at the beginning, then the partition on P2 will be just the following. So these 3 different sides of the lattice will land in different points, and the ones that are precisely in the line will land in some general point of the coordinate hyperplanes. And then once you have this, once you have this fan associated to the torus action, you can try to find something that we call the dual polytope. So you can dualize this picture. You can look at the dual polytope of this fan of cones in Q2, and then it will give you some polytope in Q2. So essentially, if you have any projective toric variety with a torus action, you can follow this procedure and create a polytope. And the polytope actually remembers the isomorphism class of the projective toric variety. So there is a theorem that, let me not attribute it to, let's say Cox. I don't want to get anyone mad in the room. But, so there is a bijection between, so here I'm jumping quite a lot of steps, but I just want to give you the feeling of what's going on. So n-dimensional, smooth projective toric varieties, smooth projective toric varieties, and n-dimensional reflexive smooth lattice polytopes. Sorry? Yes, thank you. Phannotoric. Let's write phannotoric. Thank you. Phannotoric varieties. So now let's go back to the table. So if you the table of smooth Del-Pezzo surfaces, right? You remember the ones that have GM square actions. It was P1 times P1, P2, and the blow up of P2 at the 1 point, 2 points, or 3 points. So what are the corresponding reflexive polytopes? Well, it's actually not hard to do the computation by hand in those cases, but if we list those toric Fano surfaces, so it was P2, P1 times P1, the blow up at a point of P2, the blow up at 2 points of P2, and the blow up of 3 points of P2, the polytopes that you get are simplex square, a simplex where you cut one vertex, a simplex where you cut two vertices, and an hexagon. Okay, the hexagon should be rotated if you want to be precise, but okay. So if you want to do this up to isomorphism, then you should quotient by isomorphism on the left side, and then you should quotient by GL and Z on the right side. So the polytope actually doesn't matter if you move it around with an action of GL. Sorry? Oh, yeah, reflexive means that the polar dual is still, still has lattice vertices. So the polar dual is the one that you construct by looking at all the points x in Qn, such as xy is larger or equal than -1, and for all y in the polytope. So this is what we call the polar dual of a polytope, and reflexive means that the polar dual still has lattice vertices. Okay?
Is there a unique interior point for the reflexive polytope?
Sorry?
Also like unique interior point for reflexive polytope?
What do you mean with unique interior points? I did not get that, but I'm quotienting by GLN. So that, I think that should do the trick. So if you want to do some asymptotics about the smooth Fano varieties, well, you can start doing the most naive version and start trying to count n-dimensional reflexive polytopes, n-dimensional smooth reflexive polytopes. And let me tell you something about this, which is quite curious. I think it's very interesting. So there is a conjecture. So let me write the conjecture here because I want to keep these drawings. So the conjecture is that any of these polytopes, and I should attribute it to someone, but let's say there is folklore, because I don't remember who conjectured it first. So any smooth, n-dimensional, smooth, reflexive lattice polytope, and I know I'm swapping the order of the words all the time, but sorry, it's too many words too. Lattice polytope is inside the interval -1, 1 to the nth power, up to translation and GLN. Up to translation and GL and Z. So essentially, there should be not so many reflexive smooth lattice polytopes. Well, this gives you a bound. This gives you a bound of 2 to the 3 to the n, or something like this, right? Because you have 3 to the n points in this set, right? And then they could belong or not to the polytope, right? But it gives you a very absurd bound. But I have to say that this is still even conjecture in dimension 5, if I remember, 5 and larger dimensions. This is still open. So, but we still have made some progress. So let me mention that there is work by Batirev. So Batirev classified all smooth reflexive polytopes in dimension 3. So let me just write this as a remark, because the list is much longer, and my drawing is not that good, so it's not like you will understand more if I try to draw three-dimensional lattice polytopes. So Batirev classified, so remark. So in 2000, no, in 82, in 1982, Batirev classified, let's say, a smooth toric phanotrephos. Well, in other words, lattice reflexive polytopes of a smooth lattice reflexive polytopes of dimension 3. And how many are there? There are precisely 18 of them. No, 16. Then in 2000s, or maybe 2004, in the 2000s, Krauser and Skark classified smooth toric phanophoropholes. And how many are there? 124. And then Krauser and Benjamin Neal did the same, I think around 15, so in the 15s. Krauser and Neal. Okay, same for 5 folds. And sorry, I don't remember the number. You can Google it. And something which is quite interesting for me is that in 2007, so in 2007, Ovro wrote an algorithm to classify a smooth toric Fano n-folds. A smooth toric Fano n-folds. So meaning that he wrote an algorithm that given a number n, you press enter in your computer, and after some seconds, it gives you the number of a smooth toric Fano n-folds up to isomorphism. Up to isomorphism. No, that's something I want to mention. So he doesn't assume any conjecture. He just wrote an algorithm that the algorithm works, period. So if you look at the outcome of the numbers, it looks pretty much like 10 to the n. You can guess it from this, right? So it's around 10 to the n. And it works up to n equal 11. So, well, it works in any dimension, but if you plug n equals 12, then no computer in the world can stop doing the counting. Okay? So something that I think will be interesting is anyone can look at that paper by Ovro and see if plugging this conjecture inside the algorithm will improve how fast this computation is done. So what I want to say here with this is that we have some good understanding of a smooth toric Fano varieties, especially smooth toric Fano n-folds. And even if you, so tomorrow we will discuss, or on Thursday we will discuss the singular picture, and we have like a fairly good understanding, okay? So it's something that the computer can verify for you. I have 30 more minutes, right? Yes. Okay, good. Yeah. No, what I'm mentioning here is that the algorithm you can run in a computer up to 11. If you set, the algorithm works in any dimension. So I think that just by looking at what the computer produces there, so I think that there's a way to prove this conjecture up to larger dimensions, but it's computer program. It's not like a proof. Yeah. So the argument that up to dimension 4 is like an elegant short argument using combinatorics, not like a So I think that using computer-based programs, we can prove this up to some much larger dimensions. That's a good question. I'm not sure. I'm not sure if it always terminates. No, sorry. Yeah, no. I think that there is. I think that there are going to be terminates. There is some invariant that is dropping, and it's finite, so it must terminate. But it's just super hard. So it's so hard that we don't have upper bounds. So this is something that I want to mention, that although we expect that there is something of this type, we don't have upper bounds of this shape. So we have some lower bounds which are not, let's say, not very interesting, but or maybe they have some interest. But one can prove just doing some naive countings. And let me just write this as a remark. It's not in the literature, but I have some notes on it that the number of smooth toric Fano n-folds grows at least as 5 to the n, asymptotically. Okay, so it's some remark that I wanted to make. It's just some naive counting. So it's very close to. It's like taking products and moving, like squeezing a little bit some faces. So yeah, I have discussed these questions with some combinatorialists, and they all the approaches that I have been trying give you something like 5 to the n, but we expect that it should be much faster. Let me answer that question with the following theorem. So far what we have said is that studying smooth toric Fano varieties is somewhat doable with the computer, right? I mean, you can write codes and then you can prove things by using computers. But what is the bad part of smooth toric Fanos is the following theorem. Let me attribute it to Cox as well. That a smooth, and here you can change this word by terminal, but we will discuss this on Thursday. A smooth toric Fano variety is rigid from the perspective of the formation theory. So if you want to study moduli of a smooth Fanos, and then you look at only the toric ones, you get finally many points. So you're not seeing any moduli. So this is a bit of an issue, right? If you want to conjecture, to test some conjecture, many times you want to test it in a general element on some deformation family, but this theorem tells you that the toric ones will never achieve this property, okay? So on one side, toric varieties Fano-torics are very nice because they are combinatorial. On the other side, they are not so nice because they do not have moduli. So we will come back to this in the last talk. So now let me mention a theorem that I'm not going to write the details. I mean, because it gets too long, which is the classification of a smooth Fano trifolds, right? So far we have mentioned the classification of a smooth Fano surfaces, and in the case of a smooth Fano surfaces, there are all rational varieties because they are all blow-ups of P2. And then we also mentioned that 5 of them, the 5 that I wrote in this list, are toric. The other 5 families are not toric. You can argue it using 2 different approaches. One of them is using this theorem, that smooth toric Fano varieties are rigid. And the other 5 families that I explained to you actually have moduli. Because once you blow up the 4th point on the projective space, you cannot pick an automorphism that will fix it. The 4th point will move freely, the 5th point will move freely. So when you blow up 4 or more points in the projective space, there is moduli, hence no element in the family can be toric. So that's one argument. So the second argument is that I wrote the table of automorphisms, right? And the table of automorphisms tells you that when you blow up to 3 points, the automorphism contains a tori. And when you blow up the 4th point, you get a finite automorphism. So that gives you another argument saying that these are not toric. So let me, before we jump to dimension 3, in which I will be rather brief, let me write the table one more time, and let's add more rows to it. So we have Fano, a smooth Fano surface. Here the volume, the automorphism group, and here we can ask if it is rational. I mean, we know that they're all, but let's add the row to the table, and whether they're toric. So we have two different arguments for this, right? So we say that here we have P2, volume 9, automorphism group PG L3C. It is rational. Let's check. And it's toric. Then you have either P1 times P1 or the blow up of P2 at a point. The volume is 8. Okay, we say that these are, let's say, positive. Let me just write dimension at least 2 of the automorphism group. It contains, or let's say that it contains GM squared. That's what we care about at the end. It's rational and toric. And the same happens from the blow up of 2 points and the blow up of 3 points. And then if you blow up at least 4 points, P, Q, R, S, then the answer will be the same for all of them. So only the volume will be decreasing. So here you have 7, 6, 5. So here and below, these answers stabilize. So this is finite. And finite below. This is still rational and rational below. And it's not toric and it's not toric below. Then this contains as a subgroup GM square. This contains as a subgroup GM square. And these are all rational and toric. So then the question, so this is how you classify smooth Fano surfaces. Well, maybe I can add one more column with the dimension of the moduli. So if you look at all, like the deformation family, what is the dimension of the deformation family? So the answer is 0, 0, 0, 0. Wait, I think that 0 should be, and then it should be 2, 4, 6, 8, 10. Okay, so it grows in dimension by 2. So essentially, this is just to rephrase what I just said. If you have to draw the moduli of all smooth Fano surfaces, what you should draw is 5 points, a line, a surface, a 6-fold, an 8-fold, a 10-fold. And the toric ones are just these 5 points. So if you want to test, yes, you're right. Sorry, I shifted by 1. Thank you. Yeah. 4, 6, 8. Yeah. So essentially, what we're saying is that if you want to study this moduli and test any conjecture on smooth Fano surfaces, picking the toric ones may give you some ideas, or may at least test some cases, but it sees just some points in a 8-dimensional thing when you take the union of all of them. So if I have to write the same table for a smooth Fano trifolds, I will have to write 105 rows. So we're not going to do that. But I will tell you maybe a summarized theorem, and I will attribute it to a few mathematicians, I don't want to go into all the details, but I think the version of the theorem that I'm about to write should be attributed to Skotsky, Prokhorov, Mori Mukai, and Shokurov. So theorem is Skotsky, Prokhorov. And I will tell you what each group did, Mori Mukai, and then Shokurov. And let me not write a year, but this, let's say, 90s. So they proved that there are 105 families of smooth Fano trifolds. Okay, so in dimension 2 there was 10 families of smooth Fano surfaces. In dimension 3 there are 105. Then you can ask me which ones are rational, right? In dimension 2 they were all rational. In dimension 3 we mentioned that a smooth cubic trifold is not rational. So you can ask which ones of these are rational. And this actually is a very subtle question, because rationality is not a very nice property in algebraic families. So in a smooth families, rationality specializes, but in singular families, rationality can't. I mean, if you look at the loci of rational varieties in a family of Fano varieties, the loci could not be locally closed. So it's a quite interesting set. But still, in these cases, we're somewhat safe, and what we can say is that the general point of precisely 88 families gives a rational variety, or corresponds to a rational variety. Meaning that the fiber of the family is a rational Fano variety. To a rational Fano variety. And then you can ask me which ones are toric. Well, we know this by Batirev that proved that precisely 16 of them, 16 of these 108 families are actually isolated and toric. So there are some that are isolated but non-toric, but 16 of them are isolated and toric. So precisely, so 16 families, quotes families, because just 1 point, correspond to toric Fano varieties. And this, as I said before, corresponds to a smooth lattice reflexive polytopes of dimension 3. Okay, so what is the contribution of each one of the mathematicians that I mentioned? So Iskowski and Prokhorov proved this. They classified the smooth Fano trifolds of Picard rank 1. And then later, when Mori understood the minimal model program in dimension 3 and what are the contractions between smooth trifolds, then he used this, and together with Mukai, they classified all smooth Fano trifolds of Picard rank at least 2, completing the full classification of a smooth Fano trifolds. So why I wrote Prokhorov in this set of authors? Because Shokurov is the one that gave a criteria to detect if a smooth Fano trifold is rational or not using prim varieties. And I don't think it was him. It was himself who proved the second line, but someone using this theorem proved the second line. I think I'm missing some names for sure. But this is more or less the picture in dimension 3. So then the question is, what happens in dimension 4? And that has an even shorter answer. We have no clue. That's the short answer. So question, what happens in dimension 4? So actually, Cinzia Casagrande will tell us some very beautiful theorems next week about some results that can be proved in dimension 4. But let me say that we're very far from a classification, and I suspect we're not going to see it, meaning us as a group of people, maybe the next generation. But so can we classify a smooth Fano fourfolds? And the answer is very sure. It's no. We actually don't even know how many families are there. We can get some estimates of lower bounds, for instance, by taking products and doing some very naive tricks of taking hypersurfaces in P5, and that gives you some lower bound. And I think it's not so hard to get to the thousands, okay, in terms of families. It should not be very complicated to argue that there is at least 1,000 different families of a smooth Fano fourfolds. But it's something that we do not expect to classify so far. So in this direction, I think the newest breakthrough is by Cinzia that proved the following theorem. And she will going to explain the proof, I think, maybe next week. So this was posted in 2023, published in 2024. So she proved that a smooth Fano fourfold, X with Picard rank at least 12 is a product of surfaces. So essentially, the Picard rank in some way bounds, or well, it doesn't necessarily bound, but allows you to understand the morphisms from a given variety, right? If you have different morphisms, different contractions from a given variety, then you expect that as more contractions you have, you expect, in general, a larger Picard rank. right? So controlling the Picard rank is one of the first steps if you want to understand a class of variety. So what Cynthia proved very recently is that the Picard rank of a smooth fan of fourfolds is not that large, because if it is larger than 12, it's a product of surfaces. Those surfaces must be Fano surfaces, it must be Del Pezzo, and in particular, the Picard rank of any smooth fan of fourfold is at most 18. So we get some control in the Picard rank, but we're very, very far from getting any control in the number of families. So now let me finish with a table, and then I will just mention very briefly what we will do on the next few days. So I will just summarize and explain what I will do in the next few days. Before jumping to the summary, let me, okay, maybe I'm doing too much advertising for next week, but Cynthia has another very beautiful theorem that says that if you take toric smooth, so if X is so let X be a toric, a smooth Fano n-fold, be a toric. You can write Gorenstein here, but let's just say smooth. A smooth Fano n-fold, then the Picard rank is at most twice the dimension, and if the Picard rank is actually twice the dimension, then you can prove that it's a product of surfaces, if I remember well. Or wait, no. It should be a product of P1s. Okay, anyways, there is a theorem that gives you an upper bound for the Picard rank of a smooth toric Fano varieties. So of course, we don't know how to do this for general smooth Fanos, right? We have it for a smooth toric Fanos. For a smooth Fanos, it will be a huge result if anyone can prove it in dimension 5, that there is a bound. So, sorry. If someone provides the bound, we know that there is a bound. So let me just mention like a final remark before I start finishing the talk. So a final remark is that if you look at the set of n-dimensional, smooth toric Fano varieties, right? So you can write a graph where in the horizontal line you put the Picard rank of X, and here you put the number of X's with such Picard. Okay? So in dimension 2, you don't get something very interesting. Actually, you get 1, 2, 1, 1. And if you start increasing the dimension and you rescale this picture, this at least, I mean, this is just some computational exercise that I've been playing with, but what you start getting is the normal distribution. So if you let it run up to n equal 12, n equal 10 or 9, and then you rescale, of course, you write rho x here, but you can rescale it in the interval 0, 1, 0, 1. Then you start approximating some normal distribution. So these are, there is a lot of open questions about what are the asymptotics of n-dimensional Fano varieties. And the truth is that we do not have any expectation yet. Maybe toric ones can help, but at the same time, toric ones do not help a lot because they do not have moduli. So let me tell you, let me summarize what we did today, and then I will tell you the proposal of what should be done instead. Okay, so let me write a final table, and then I will tell you what we will be doing in the next 3 days of this mini course. So we can visit again the number of families of Fano varieties. So let me write here n, which will be the dimension. Here I will write the number of families. And here I will write if there rational, and here we will write if they are toric. So when I write rational and toric, I always mean the general element of the family, because as I was saying before, deciding if all the elements of the family are rational is a very complicated problem. It's even open in some cases of dimension 3. So in dimension 1, there is just one Fano variety, P1, which is rational and toric. In dimension 2, well, I'm just rewriting what I wrote before. There are 10 families. All of them are rational. 5 elements are toric. In dimension 3, the number of families is 105. 88 have a rational general element, and 16 of them are toric. In dimension 4, who knows? Who knows? 124. So something interesting about this table is that if I keep writing down, I will just write question marks here and below. But I can actually write like 7. I can write 7 more steps here. So the natural question that comes to mind is, can we find some definition between toricness and rationality in which we can fill the whole column? So this is what we're going to do on Friday. Can we come with a definition that lies exactly, well, I don't know what exactly means here, but lies between toric and rational, but we can prove somehow that most Fano varieties will have this property. So this is what I will talk about on Friday, and this will be the object that will be defined on Friday, that are these cluster Fano varieties. Okay, so this is related to cluster algebras, but do not worry, I do not remember the definition of cluster algebra, so I'm not going to give it. Okay, so let me just tell you that tomorrow we will be discussing about log terminal singularities, and then on Thursday I will try to do the same table, but then we will start talking about singular Fano varieties and I will explain you what can we feel in each dimension about different singular kinds of Fano varieties, and then on Friday, on the final day, we will define this notion of cluster Fano varieties, and I will explain how they fit nicely between toric and rational. And the advantage is that they can still be explained combinatorially, but they also have moduli. So they sort of win over toric varieties in these two senses. So let me just write what is the aim of this mini course. So the aim is to introduce a new notion of Fano of varieties, introduce a new notion of algebraic varieties that lies between rational and toric. So I'm not going to give the definition now, but these varieties will be called cluster type varieties. Are already in the literature, are called, quotes, cluster type varieties. And we will study the moduli and the description of cluster Fano varieties, and study cluster Fano varieties. Okay, but before we get here, because to get here we will actually have to discuss about singular Fano varieties. So before we get to the aim, which we'll mostly do on Thursday, we'll be discussing about log terminal singularities tomorrow and Fano varieties with log terminal singularities. And at the end, we will introduce this new class of algebraic varieties on Friday, and I will tell you how you can use it to, well, to be honest, we still don't have this column, but at least we're developing technology and theorems that will lead to this in the future. Okay, I will stop here.